Hello, everyone, and welcome here to the Doxsteel Fasteners Hydrogen Embrittlement webinar. I'm your moderator, Chris Skelton. Doxsteel Fasteners' mission is to revolutionize bolt theory and practice in the fastener industry. It's our goal to consistently conceptualize and deliver safer, less expensive, and more scientifically sound bolts to the industry. Doxsteel fasteners have demonstrable advantages over other bolts in the market, including 20 times your return on investment, 21 years of fastener life expectancy, and 0 hot bolting required. We have a very exciting webinar for you guys today on the science behind hydrogen embrittlement and some pragmatic solutions to potential issues in the field. Many of you tuning in may have an understanding of hydrogen embrittlement, but may not know everything there is to know about it or know the seriousness of the issue. So we've developed this presentation as a way to sort of unpack that. There will be time for a Q&A with our 2 experts here at the end in case we missed anything. As the webinar goes forward, you'll see a Q&A. You'll see a Q&A button at the top of your screen. Just click on that. If a question pops up, just type it on in, and then at the end of the webinar, we'll take a look at all those questions and address them with whatever time we have left. This webinar is also going to be the first in a line of webinars that we have planned as part of our efforts to expand the knowledge of the industry and to improve communication and knowledge sharing between verticals on a variety of topics. In addition, we want to make sure that those in the office are connected to those in the field. We'll make sure to send out an email to register for our next webinar when it comes closer, and we'll also post that update on our website and on all of our social media channels. I definitely encourage everyone listening in today to join our LinkedIn group, which we've created called the Cost of Bolt Failure. We hold ongoing discussions in there about how fasteners can help companies save time, money, and lives. We also host lunch and learns. So if you're interested in bringing in your teams to our offices to talk more on these subjects, please feel free to reach out after the webinar via our website, which is doxsteel.com, and follow our company page, Doxsteel Fasteners, on LinkedIn. So without further ado, allow me to introduce our 2 speakers for today. The first is going to be Dr. Jim Burke. Dr. Burke has worked in the oil and gas industry for more than 46 years, and most of those years were spent between BP and Shell in various technical and research leadership positions that dealt with materials, corrosion, welding, drilling, production, refining, operations, and major projects in the upstream and downstream parts of the major operators. Jim received his PhD in metallurgical engineering from the University of Illinois with a minor in applied mechanics, and he served in both leadership and member capacities on more than 30 industry committees and advisory boards. His work is in more than 25 publications, and he's presented at more than 30 national and international conferences, including an invited lecture at the 2016 International Conference on Hydrogen in Metals. He's now an emeritus member of the API SC 20 and 21 subcommittees on quality and materials. Say hello, Jim.
So, hello everyone. I've really been looking forward to this webinar today when we'll be discussing hydrogen embrittlement. So thank you, Chris.
Absolutely. So our second speaker today is going to be Dr. Omar Rose. Omar is the senior corrosion expert here at Doxsteel Fasteners, and a lot of what you'll see here today is based on his research here at Doxsteel, and his work directly impacts the overall performance of our products. Omar earned his PhD in materials science and engineering from Penn State, where he worked in corrosion modeling for nuclear reactors at their Center for Electrochemical Science and Technology. He also worked on microbiologically influenced corrosion at the University of Toulouse in France, and most recently he was a research scientist in oil and gas corrosion at the University of Akron. He's an active member of several corrosion associations, including NACE, ECS, and ISE, and has had his work published at both conferences and in peer-reviewed journals. His fields of expertise include materials, metallurgy, electrochemistry, and corrosion, and his main interests and efforts are to develop a better understanding of corrosion phenomena. Say hi, Omar.
Hello, everyone. Hello, Chris. Hello, Jim. I'm very glad to be here and show you the efforts that we're doing at Doxsteel Fasteners to address the problem of hydrogen embrittlement. This is just an introduction to that problem, but I think it's going to be very useful for everybody else.
Excellent.
Thank you.
So let me go ahead and outline kind of what today's agenda is for the webinar. It's going to be broken down into 4 sections. First, we're going to unpack 4 hydrogen embrittlement failure case studies. These are situations where the failure was catastrophic or had something that led to hydrogen embrittlement and really cost companies due to its occurrence. Then we're going to go into some details on how hydrogen embrittlement happens and how it affects the operations, and then experimentation we've done here at Doxsteel Fasteners to determine the odds of hydrogen embrittlement affecting bolts when they're using different coatings, and the current work we do here at Doxsteel to prevent hydrogen embrittlement in the current environment. So without further ado, I'm going to hand this off over to Jim, and he's going to get us started.
Okay, thanks, Chris. And just to get started, as Chris points out, we need a little bit of context. And so we're going to talk about 3 offshore industry failures, and then a 4th, something that's, I guess, onshore. It's a bridge in the San Francisco area. One thing that I think you'll see that's a common point of these failures, they're catastrophic. What do we mean by catastrophic? They create a huge amount of damage. They're rather surprising. People do not expect them because hydrogen embrittlement is a failure mode or a failure mechanism that's not considered in many cases by designers. It leads to, in our context, equipment failures, drilling equipment failures, and it provides significant safety risk to the personnel in the operations, and also leads to environmental risk. That is the leaking of production fluids into the offshore environment. And these failures that we'll be talking about, you'll see that they occur mostly in the subsea environment. In other words, they require seawater or water to make the mechanism viable. We'll talk about that a little bit later too. Here you see a picture of a Generation 5 dual derrick drilling ship. I just wanted to show this to give you the size of the equipment that we're dealing with in these types of failures. This is bigger than a World War II battleship such as the Iowa or the Missouri, but it's smaller in terms of displacement than a Nimitz-class aircraft carrier. So it is a significant piece of equipment, and the drilling equipment hangs from these derricks. We'll be talking about high-strength bolting. For those who are familiar with the grades, these would be like grades 125 and higher, 125 KSI. The lower grades, the 60s and the 80 grade bolting, which are used on pressurized piping on topsides and in onshore plant environments, are typically not subject to hydrogen embrittlement because the strengths are much lower and the heat treatments don't lead to high hardness materials. So I mentioned we will be looking at 3 offshore failures, and you can see a schematic here with this dual derrick drill ship, a marine riser, a lower marine riser package, a BOP, and then finally the ocean floor. The first failure occurred about mid-water depth in this drilling riser, and it was a failure here at the flange. The second failure that occurred, the first failure occurred on this actual dual derrick drilling ship. The second failure occurred on a different rig in the lower marine riser package, and the third one occurred in the BOP, which is just below the marine riser package, okay? We depend upon these riser connections to control the drilling fluids and maintain pressure and fluid integrity between the drilling environment inside the pipe and the ocean. The LMRP controls the operation of the BOP and other equipment that is down at the bottom of the ocean in this lower marine riser package. And then the BOP is, of course, a safety device that shuts off the well or the annulus. So all these are very, very important devices, and we'll be talking about, too much. Excuse me, my finger is a little bit too heavy. Now, you can see in the illustration that we're showing this drilling riser parting right here at the flange connection. And this was a catastrophic failure, as we say. It just all of a sudden lets loose. And it's like if you've ever stretched a rubber band and made the mistake of cutting it, you know the rubber band will accelerate both, in this case, upwards or downwards in the case of the riser. The riser slingshots up and rebounds into the derrick at the top of the rig. And then the bottom part rebounds into the resistance of the LMRP, the blowout preventer, and the bottom of the ocean, and then just because it's unsupported, falls to the side. Well, the top simply hangs there. This was a failure of some insert bolting, much like a nut, and it was we had a presence of thermally sprayed aluminum, which is a sacrificial coating in an offshore environment. The repair of this device, this drilling rig assembly, ran on the order of $400 million, and the lower part of the riser, which you see toppling here again, just missed over $500 million worth of subsea equipment that had been installed but was not in production. So when we say that the failures are catastrophic, they're catastrophic in the actual failure in itself. They're catastrophic in terms of some of the economic impact. It's shown here in this one, and there can be a risk to environment. So just to play on this failure one again, you can see the illustration here of the connection, which is a flange connection with 6 bolts. These bolts were 3.5 inches in diameter. For those that are familiar with some of the metallurgy, they were AISI 4340 or ASTM grade. It was an L43. And here you can see the bottoms of the inserts and bolts peeking out from the top of the flange from this connection up here. And then here you can see the bottom. This was, of course, hanging in the from the drill ship at this time. Picture was taken by a swimmer, subsea unmanned submarine, and then here you can see the bottom. There's several holes here. There's this bolting pattern of 6. The larger holes are where the bolts went through and the nuts broke off on the bottom. The other holes are for service lines and control lines, mud and choke and kill lines. So that's a kind of a summary of the first failure. We found that all the harnesses were over Rockwell C35. The second failure occurred in the lower marine riser package, and it was on a different drill ship almost 9 years, well, 10 years, almost 10 years later. And here, again, we show the location of where the failure was. We show the illustration of what the lower marine riser package looks like. And just for convenience, we won't go into all that. But there's a flange up here that failed. And then here are the BOPs here, right here below. But this is part of the lower marine riser package flange. You can see the bolt sticking out here, and you can see where they fit up. This is a 5.5 inch diameter drilling line or drilling tubulars. This, after it had failed, we had communications with potential communications with the production play, and could have been a severe environmental impact, but that did not occur, fortunately. And then the final offshore failure we're going to talk about is the blowout preventer. It was, again, a flange bolt failure, as the second one was, and the first one was. You can see the drilling riser again and where the BOP is. And then here's the top flange as it's taken offshore. You can see from the illustration of how these studs with their nuts on them here in the illustration are standing up proud. And here's the failure. There's the flange, and there's where the bolts are standing up proud again. And you're missing some bolts around the one side. That's where we've had the hydrogen embrittlement failures. And you can see the failure of this stud. It's instead of occurring down at the base like the rest of the sister studs did, it failed up near the top where the nut was bolting this assembly together. Now, these bolts over here did not fail. However, these did. This did not result in a separation until it got on the drilling rig floor when they pulled the string. One thing, though, I want you to take a look at, there's a shiny area on these studs. These are studs that have been taken out. And then there's an area here where they're missing the zinc. And that'll be important and subsequently, you see when my colleague Omar Rose talks about hydrogen embrittlement mechanisms and how to prevent it. Again, we had high hardness in excess of 35. And there was something that turned up that was new in this failure that we learned about, which was segregation and hard and soft zones. So that when you made a hard measurement of these bolts, you got a low hardness, which you wouldn't expect to have failure. But when you actually looked at where the failures did occur, the cracking did occur, the hardnesses were in excess of 35, 34. So the fourth failure I'd like to talk about, I mentioned 4, is the Bay Area Bridge failure. This is, of course, in San Francisco Bay. It goes from Oakland across to Treasure Island, I believe. I've written on it. The bolting here, bolting was located here in these areas on the bridge. It was a high-strength structural grade bolting, ASTM A490, Rockwell C39, and the bolting industry for construction onshore has found that Rockwell C39 is acceptable for these types of applications. These bolts were hot dip galvanized. You can see them here. And here's an inspector who's looking at them after the first failures occurred. Again, like the other bolts we said, these are very large bolts, 3.5 inches in diameter. And this is actually a failed bolt. You can see the failure surface or fracture surface here. And the difference in this failure is the previous first 3 were in-service failures, where we were losing zinc or aluminum, which is a sacrificial coating that can generate hydrogen, and then in service. This occurred during the initial installation of the bridges and torquing them up and then finding them having popped or broken, brittly, catastrophically like glass. This led to somewhere around $70 or $80 million worth of repairs. It was not very much damage as we'd seen in the offshore examples, but just the replacement of the bridge bolts. And again, $70 or $80 million, that's a significant amount of money. And the second point is the Bay Area Bridge was closed for very, very many months in fixing this. And this led to a lot of additional costs for transportation and commerce for not being able to use the bridge. So again, it's a very costly event. This hydrogen, or this failure, because in hydrogen embrittlement, of course, you have to have hydrogen. This hydrogen, we believe, came from the manufacturing process. And Dr. Rosas is going to talk about the manufacturing process and then the in-service conditions that lead to hydrogen a little bit later. Okay, now to kind of string all this together, I'd like you to meet the players and give you an update on where we are right now and how we got there. So you've seen the first failure. That happened in May of 2003 towards, well, it happened over the Memorial Day weekend. I was involved. I actually led the analysis of this failure. Then we got the results, and it was decided to share the results with the industry. This information was presented at a joint meeting in Houston of NACE and ASTM in January of 2014. And again, it was presented at the Independent Association of Drilling Contractors in February or May of 2004. I'm sure most of you know what NACE stands for, National Association of Corrosion Engineers, and then ASM, American Society for Metals. So again, there's getting to be some interest in industry groups. We then had a hiatus from failures for, well, 9 or 10 years, as I mentioned before. And then we had failure 2, which again was a hydrogen embrittlement catastrophic failure. Occurred in December of 2012, very near the end of the month. Then along came failure 3, which occurred at the very beginning of July in 2014. So this number of failures, since they were occurring in the Gulf of Mexico, caused Bessie, which is a part of the Department of the Interior, to have some concerns as they regulate the safety and environment in the Gulf of Mexico. All 3 of these failures that I mentioned occurred in the Gulf, and Bessie was involved, of course, in each one and gave the go-ahead to go back to work. But these things are starting to become there are too many of them, and I think the industry wanted to get a handle on them. So Bessie put together this QFIT report, and I believe there's over 14 failures in there that are summarized that are both in the Gulf. There are 5 in the Gulf with carbon steel and 1 with a CRA, and the rest are around the world. They're similar failures to failures 1, 2, and 3 in the sense that they're hydrogen embrittlement failures. So with that report, API, being an overarching organization that covers things not just in the Gulf but worldwide, decided to form a bolting task force. And they invited industry experts to participate in this. And this had the attention up to the chairman of API. And the group met for over a year and put together what they refer to as a failure mapping or a threat mapping of all the different types of failures that you could have in bolting, especially in offshore drilling equipment, high strength bolting. And recommendations were made, task group recommendations, and after everyone had a chance to review the recommendations from the task force through API, the chairman of API sent a cover letter with the report to Bessie. I like to mention that both of these are Googleable. You can Google them on the internet, and get them for yourselves and look at them if you're interested. So, of these task group recommendations, TGRs, there are over 20 of them. TGR 3 recommended that zinc not be used in service for these bolting because of the evidence that had been found of zinc or aluminum being present in these hydrogen embrittlement failures, the ones that I referred to. If you look at the QFIT report, you'll see that they also found additional evidence there. So Bessie accepts these recommendations, and API initiates these activities through the executive committee, and the chair of the executive committee directs each of the subcommittees to cover the task group recommendations that are in their area of technical expertise. CSOEM is the Committee for Standards, Engineering and Materials, and of course the SCs are the subcommittees. Some of that work is currently being done in task groups, TGR3, TGR4, TGR7, and TGR8. So besides participating in the API bolting task group, I also am a current participant or chair in leading some of these efforts in the industry, API. So Bessie is participating in this along with the API chairs and the technical experts for the industry. All right, so that's kind of how we got to where we are and how we've identified what the real issues are, what we need to address. And it's being done in a very logical manner through API with Bessie's support and concurrence. So now we've had a little bit of time to see why is hydrogen embrittlement important. Now we're going to go into a little bit more about what is hydrogen embrittlement. And, you know, I've already mentioned it's a catastrophic failure. It just, well, it's a slide here says it's the mortal enemy of fasteners. It just causes the fastener or the bolting in the stud to fail under very, very low loads. And it just fails like glass. And this is a very dangerous thing, of course. They fracture easily. And the thing that has been learned, this has been known for over 100 years in one form or another. And it's caused by the tensile stress, the material susceptibility to hydrogen, and the corrosive environment. So here we are. You see the stress in the blue circle, the environment in the yellow circle, and the material susceptibility in the dark gray charcoal surface. So what does this really mean in terms of real applications? Well, the stress comes from the bolting load during torquing. The API Subcommittee 16 has issued a document that says that, for example, these flange bolts that you've seen need to be bolted at 2/3 of minimum yield strength. So that sets a stress. That's a fairly high stress. And the torquing, which is not going to be a subject of this webinar, but I believe Docs plans to have another one addressing that. The torquing can vary and cause the loads to vary by as much as plus or minus 30%. So you have a possibility of getting very high stresses. Now, the environment is generated from corrosion or hydrogen embrittlement. Omar will be talking more about that specifically. And then the material susceptibility, it's the hardness. And you measure that on a number of different hardness scales. Rockwell scale C or HRC sometimes, Rockwell C. We measure Brunel, we measure Vickers. You may have heard these also. But again, hydrogen embrittlement occurs in high strength materials with hardnesses well over 34, 35. And the material breaks, the higher the hardness, the more susceptibility and the quicker the failure will occur. So when these three things, the high stress, the high amounts of hydrogen, and the high hardness come together, then you have hydrogen embrittlement. If any one of these factors are not there, you have very low stress, the material is soft, that is below Rockwell C34, or you do not have any hydrogen, then you will not have hydrogen embrittlement. So you have to have these three conditions that occur. You can see the overlap of these three circles. These are called Venn diagrams for those that are interested. And when all those three conditions, again, are present, then you have sufficient cause to lead to hydrogen embrittlement. Okay, I think we know where the stress comes from and where the material susceptibility, that is the hardness. So let's talk about how we get the hydrogen in there. And we have a very simplified caricature of this, or cartoon. You can see that we are forming hydrogen at different places. The hydrogen forms out in the seawater and then attaches itself to the surface. And some of it moves into steel, and some of it recombines with electrons and bubbles off as hydrogen. So we have a fraction of the hydrogen going into the steel and a fraction bubbling off. Now, the hydrogen likes to align itself at the crack tip or notch tip in terms of threaded connections, such as bolting or studs. When the hydrogen concentrates itself at the crack tip or notch tip, then the bonds between the iron, the atomic bonds between the iron, become weakened. And there's various mechanisms or ways that happens, which really, to us, is not as important as the fact that when hydrogen is present, it enters the material, it concentrates at the crack root, and then causes cracking, as you see here in the schematic. Now, some people feel that, oh, well, we only put a few atoms of hydrogen in there, 10 parts per million or 20 parts per million. When steel makers make forgings or plate steels, they guarantee that the hydrogen concentration is less than 2 parts per million. And then we typically find that that's a safe level. But with this hydrogen embrittlement in seawater, we can get concentrations greater than that. And we can get concentrations generated by zinc or aluminum, which are much greater than that. Anyhow, we can have a concentration of hydrogen of 2 parts per million in the material away from the crack tip, up in here, but the concentration down in here is usually 100 to 1,000 times or more greater. So we may have 2 ppm in the bulk, even with some charging, but we will have 200 or 300 to 1,000 ppm at the root. And this can really cause problems, especially in the high-strength steels. So I think that's a little overview of hydrogen embrittlement in action. Here's an example of how hydrogen worsens crack growth. So on one scale here, we have the average crack size, and that's in micro meters squared. It's an area. So that's 10 to the minus 6 meters squared. And this is the local plasticity that you have in a test bar that you're straining, you're pulling apart in a load machine. And as you strain it, it gets longer. But you can notice that the steel that has hydrogen in there, it only gets about 6 or 7% longer before it actually breaks. Before the crack areas, average crack area, starts to really get large relative to the stable crack growth when you're pulling it. Now, the material that doesn't have the hydrogen in it will achieve a much longer elongation. That means it'll get, a third longer than it originally was before it will finally crack due to just normal plasticity, like salt water. One is saltwater taffy, and one is glass. The Berlin, of course, is glass with the hydrogen, and the ductile one is the saltwater taffy. So I hope that's giving you a little bit of flavor for why hydrogen embrittlement is important, and also what it is.
All right, thank you, Jim. So as Jim said, hopefully that's given you a good overview as to the importance of hydrogen embrittlement, or rather the dangers of it. and why it really is the job of everyone in the industry. You can see the industry's come together and has decided we really want to tackle this issue and make sure that it happens as little as possible, if at all, hopefully. So without further ado, I'm going to turn things over to Omar, and he's going to describe some of the things we do here at Doxsteel to take care of hydrogen embrittlement and make sure that it doesn't happen to our fasteners. And I want to remind you guys at this time, I see some of you have already submitted a couple of questions in the Q&A. That's excellent. Just keep doing them more as you know, questions you have pop up. Type them in the Q&A, and we'll get to them at the end. All right, take it away, Omar.
Thank you, Chris. Thank you, Jim. Well, Dr. Jim Burke just showed us how dangerous is hydrogen in our materials and the brutal consequences of having this hydrogen in materials and in operations. He also mentioned that hydrogen is coming from somewhere, and that's a very natural question. If hydrogen is so dangerous, well, we have to know from where this hydrogen is coming from. In fasteners, there are two main sources of hydrogen: the manufacturing process and the service conditions, and I'm going to describe both. With regards to the manufacturing process, there are several steps in the process that produce hydrogen. For example, pickling, phosphating, plating. Those operations produce naturally hydrogen as a parallel reaction. And at Doxsteel Fasteners, we're doing our best to reduce to the minimum the risk of hydrogen. This is critical for us. And there are several steps we can also take to reduce that risk. And that takes us from the very beginning of the process, getting the material, to the very end. And I'm going to explain to you. For example, by complying the API 20E standard, we guarantee that our material is not going to be susceptible to hydrogen. In addition to that, an extra layer of protection is complying to the ASTM V994 standard. That's specifically for nickel-cobalt, and it guarantees that the plating process is not going to induce hydrogen into the material. Finally, when we have our final product, we follow the ASTM F519 standard to test if the material suffers some hydrogen induction. I'm going to explain to you. The ASTM F519 standard tries to bring together all those failure parameters that Dr. Burke mentioned. And for example, it uses a very hard material that is around 50 Rockwell C, and it suggests to use a load of 75% of the ultimate tensile strength during 200 hours. So we have the material susceptibility and we have the stress. So there is one thing missing in the equation for failure, and that's the environment. That is the objective of this test, is to know if hydrogen was inside the material. So if the material breaks before the 200 hours, that means that the plating process induced hydrogen in the material. Otherwise, the material is hydrogen-free. So at Doxsteel Fasteners, we do this kind of tests every 30 days to all our batches. And so far, we haven't had any failure or any rejection, which proves that the nickel-cobalt plating at Doxsteel Fasteners is not inducing hydrogen. And how important is that? Well, just remember what Dr. Burke showed us about the San Francisco Bridge. That was a failure due to a manufacturing process. The manufacturing process induced hydrogen. And that's how important it is. So we're trying to eliminate the hydrogen from the manufacturing process. But we're also worried in addressing the service conditions. So before I explain you the test and what we do for service conditions, I'm going to introduce you three concepts that are going to be very helpful to understand the materials behavior in certain environments and how they produce hydrogen. And these concepts are potential, current, and something we call the sweet spot. So potential is the energy that every metallic material has when interacting in an environment. Current is also a consequence of that interaction, is how many electrons the material is exchanging with the environment, with the surroundings. So it's trying to reach a dynamic equilibrium. In terms of corrosion, potential is the corrosion energy. The higher the potential, the more resistant the material is going to be to corrode. For example, gold, platinum, palladium, those materials that are noble, they have very high potentials, very positive potentials, and they don't corrode. On the other hand, zinc, aluminum, magnesium, those materials have very low potential or negative potential, and they corrode easily. Current tells us how reactive a material is. Again, it's exchanging electrons. It's telling us how fast our material is going to interact with the environment. So for the case of hydrogen, the higher the current, the higher the hydrogen that is going to be produced. The sweet spot, it's a value of potential where no corrosion occurs. So no electrons involving corrosion reactions are exchanged. Not all materials are in this protection potential. So we have to apply certain energy, certain potential to take those materials to that sweet spot. The problem is that when we are reaching that sweet spot, there are reactions happening around it. And we know that potential values more negative than that sweet spot are going to produce hydrogen. So I'm going to show you the importance and the relationship of potential in hydrogen production with the next slide. This slide is a plot of the crack growth rate at different potentials for materials with different strengths, for high strength in blue to low strength in yellow. I want you to notice 3 points of interest in this plot. The first one is this black arrow pointing out minus 0.85. That's our sweet spot. That's where we want to be. That's our protection potential. The other 2 points of interest are this white area and this pink area. And the interesting of those areas are the experimental data in there. It's notorious and obvious that the experimental data in the pink area has a steeper slope, which means that the crack growth is faster, it's easier. And that is because the different electrochemical reactions happening around the sweet spot to the left and to the right. So to the left of the right spot in this white area, what happens is that we are applying the energy, that potential, but we're not quite there. We are not reaching the sweet spot. So what happens is metallic dissolution. There is an anodic stress corrosion cracking, for example. That's how the crack can grow. If we apply more potential than this, and we overpass the sweet spot, then we go to a dangerous zone, because the reaction in the pink area is hydrogen production. And as Dr. Burke showed us, hydrogen can penetrate into the material, go into the crack tip, and make the material very weak. So by applying a protection to the material, and if we accidentally apply more than what needed, we're producing or inducing a more aggressive damage to the material. An everyday analogy that I always helps me to understand this is a diabetic person on insulin. If that person takes the medication and the dosage is not correct, that person is going to still be suffering of diabetes, not regulating the sugar in the blood. If that person tries to compensate that and takes an overdose, then can go here, and then it can produce glaucoma that is losing the ability to see. So by compensating or trying to protect more, it's creating a more aggressive damage. And that is important for us because that happens every day we apply cathodic protection or we use sacrificial coatings because they live in this range of potentials. So now that I showed you the importance of potential current and I talk about sacrificial coatings and cathodic protection, let's do that. Let's talk about galvanic coupling by sacrificial coatings, and afterwards, let's talk about cathodic protection, what happens. So what we did to test the galvanic coupling was this experimental sweep that is potential. Again, remember the potential is the corrosion energy, and current. Current is how much a material is going to react. So this plot of bare steel, nickel-cobalt in blue, zinc in yellow, and zinc-nickel in red showed us the kinetic behavior of those materials in the same environment. So this plot is used to see how much a material is going to react in certain environment, but also can give us information about potential. For example, that is the first thing we have to notice. The potential of the nickel-cobalt here, it's more positive or less negative than in sacrificial coatings. And remember that the higher the potential, the more noble the material is. So there's not going to be corrosion or much less corrosion for the nickel-cobalt. The sacrificial coatings are way below, even below this black horizontal line. This black horizontal line is the sweet spot. And remember that we said that everything below the sweet spot, everything more negative than the sweet spot is going to produce hydrogen. So the analysis on potential here is telling us that nickel-cobalt is not going to produce hydrogen, but sacrificial coatings are going to produce hydrogen. The second thing I want you to notice is the values of the current. So again, current is how reactive a material is, and we can see that nickel-cobalt delivers a very low current compared to zinc and zinc-nickel. Please notice that the scale of this current is logarithmic. It means that every unit, there is a 10 times multiplier. So that means that zinc is 10 times higher than nickel-cobalt, and zinc-nickel almost 100 times more than nickel-cobalt. This shows the activity of those materials. And if we relate this to the potential, we know that sacrificial coatings are producing hydrogen. And based on this current, they're very active. So they are producing too much hydrogen. Let me summarize this plot with this table. Nickel-cobalt has a very high potential, a very low current. It's very resistant to corrosion, and it produces no hydrogen. On the other hand, zinc coatings or sacrificial coatings in general have very low potential. They deliver a lot of current, very high current. They are poorly resistant, and they release a lot of hydrogen. So this is important thing regarding the kinetic analysis. The kinetics is telling us, well, you know, nickel-cobalt is going to be a slow kinetics, while zinc coatings are going to be very fast. We can also perform a thermodynamic analysis. This is a plot of the potential again versus the pH. This is for iron or steel, for example. So we can overlap here this blue area. This blue area is the water stability region. This is where water lives happily as H2O or ionic form, and it does not form gases. However, away from that area, for example, below this area, there is hydrogen production. Everything lying below that water stability region is going to produce hydrogen. If we overlap our materials, then we can see that a nickel-cobalt, because of the values of potential, nickel-cobalt is in the water stability region, is not going to produce hydrogen when interacting with steel. On the other hand, zinc coatings are going to produce hydrogen when interacting with steel. So the kinetics and the thermodynamics are telling us that sacrificial coatings are going to produce hydrogen, and that increases the risk of having hydrogen embrittlement. Another way to see this plot, the potential thermodynamic plot, is the galvanic series. I call this the materials corrosion map because they look, I overlap the hydrogen production zone or region at pH 7.5, and it looked like a map where all the black squares, including nickel-cobalt, are safe of hydrogen. They are in the shores. And the hydrogen that is the blue square, we can see some materials, all the sacrificial materials are producing hydrogen, are drowning in this ocean of hydrogen. So that's what I see it as a corrosion map. So again, sacrificial alloys are going to promote hydrogen embrittlement, while nickel-cobalt, since it's not sacrificial, is not going to produce any hydrogen. So we can make some remarks here based on the analysis that we just performed. Zinc coatings are going to produce hydrogen because that's the common cathodic reaction, and that leads to hydrogen embrittlement. The thermodynamic analysis shows that nickel-cobalt is not going to produce hydrogen, and using sacrificial coatings, is going to increase the risk of having hydrogen embrittlement. Now that we talk about this analysis of galvanic coupling using sacrificial coatings, we're also concerned to the other source of hydrogen that in the service conditions, that is cathodic protection. In the cathodic protection, no matter what, no matter the potential of the material, we're always going to force to have hydrogen. Just a reminder of what cathodic protection is. In cathodic protection, we're supplying electrons to the material to make it a cathode, and cathodic reactions happen there. Cathodic reactions are the opposite to anodic reactions or oxidation reactions. So we are stopping corrosion. The problem is that the typical cathodic reaction is the hydrogen production. So again, we are protecting the material, but we are forcing hydrogen to be produced and increasing the risk of hydrogen embrittlement. So we perform 3 types of experiments with cathodic protection: an electrochemical experiment, a mechanical experiment, mechanical resistance, and permeation test. And I'm going to show you all of them. So first, the electrochemical results. On to the left, we can see the polarization resistance of the 3 materials we're talking about. The polarization resistance tells us how difficult a reaction is going to happen, is going to be. It's, for example, a slope in a hill. If the slope is too steep, then it's complicated to climb it. It's the same for the materials. If the polarization resistance is too high, it takes the reactions are lazy, so they don't go there. They go to the less resistant material. And we can see that nickel-cobalt offers the highest polarization resistance, even when we are producing an over cathodic protection. On the same token, the cathodic current, remember the more current we have, the more hydrogen we have. Current is telling us that sacrificial coatings under cathodic protection are going to produce more hydrogen, are going to have more current than nickel-cobalt. Nickel-cobalt is not, it's poorly reactive with hydrogen. The kinetics is slow compared to the other materials. So hydrogen is not produced, and there is no exchange of electrons, and hydrogen is not being produced. That is regarding the electrochemical analysis. We did the same for a mechanical test. In a modified F519 ASTM, we took some tensile samples with a notch, with a stress concentrator, and we put them 30 days under cathodic protection of minus 1.0 volt. You can see here in the images all the hydrogen being formed on bare steel, on zinc coatings, and on nickel-cobalt. It's dramatic, all the hydrogen formed on the zinc. So after 30 days of cathodic protection, we just broke the samples, and these are the results. I want you to notice 2 things here: the materials without cathodic protection and with cathodic protection. So first, the blue squares, that is the material without cathodic protection. We can notice that the zinc coating reduced the mechanical strength just by applying the coating, reduced the mechanical strength in a 25%. That didn't happen on the nickel-cobalt, which indicates that nickel-cobalt plating had minimal effect on the mechanical performance. Now, when we apply cathodic protection, the results were dramatic. In both cases, bare steel and zinc coating, the mechanical resistance dropped 50% under cathodic protection, while in the nickel-cobalt, the resistance was the same. So nickel-cobalt plating does not produce hydrogen during manufacturing, and nickel-cobalt protects fasteners under the stress and hydrogen conditions. So that test shows that nickel-cobalt is a barrier to hydrogen. Hydrogen is being formed on the surface, but is not penetrating even when we create a stress concentrator. Just to prove that and to quantify how much hydrogen is actually passing, we're performing permeation tests. The permeation test is very straightforward. On one side of this is the steel, we're forcing the formation of hydrogen. This hydrogen is crossing the steel and passing to the other side. On the other side, we account for the current that is being produced by the oxidation of this hydrogen, and then we know how much hydrogen actually passed. So this is a schematic of the permeation cell. It's a double cell where we can see on the left, we can see the charging cell. And on the right, we can see the exit cell. The specimen is right here in the red zone. And this is for nickel-cobalt. This is an image for the nickel-cobalt experiment. We didn't see any hydrogen being formed there. We did the same for bare steel, and we saw some bubbles of hydrogen. And when we did the same for zinc coating, the difference was, again, dramatic. So again, we measured the current on the exit side, and these were the results for the permeation according to ASTM G148. So again, we can make the difference of using cathodic protection or not. For both bare steel and zinc coating, using cathodic protection produced a higher permeation. And that's because there was more hydrogen being produced, and the concentration of hydrogen allowed to penetrate more the material. Since nickel-cobalt did not form any hydrogen, or not enough to be detected on the exit side, the permeation was 0. But maybe these numbers are not telling us too much because they are like very small and similar. So I'm gonna show you a short video. I'm gonna mute it here. I'm gonna show you a short video of an accelerated test for hydrogen production. So we're using a solution with a very low pH, and we're testing for different materials: zinc nickel, zinc plated, nickel cobalt, and cadmium. So we can see immediately how the sacrificial coatings, well, in this case zinc, starts reacting with the solution. For cadmium, it takes like 5 minutes, and we are gonna see that at the very end of the video. But the difference of nickel cobalt and zinc nickel, it's quite considerable, it's quite obvious. We can see the bubbles here. There's a burst of bubbles right here, and even fumes over here. That's for one stock, and that's how much they produce. We also perform some measurements of hydrogen calculation, and it's 75 milliliters per 20 centimeters square. So after 5 minutes, the zinc is depleted. The only way we can stop the hydrogen production is because the zinc is gone. And for CAD, we can see here that hydrogen is being produced. So the kinetics of cadmium is a little slower than zinc, but in the end, it's going to produce the hydrogen. So just to wrap up this information, we want to say that Doxsteel fasteners are manufactured and coated without producing any hydrogen. We tested that in our manufacturing process. We have tests that prove that. Nickel-cobalt is not a sacrificial coating, so it's not going to produce hydrogen because of the high potential and because it's not reacting, it's inert to hydrogen. So nickel-cobalt is going to protect from external sources of hydrogen, such as cathodic protection. It's not interfering with cathodic protection, but it's not actually forming the hydrogen. So it's allowing the passage of cathodic protection, but not forming hydrogen. So we want to do this analogy or similarity with the Venn diagram that Dr. Burke showed us, where we have the environment, the stress, and the material susceptibility. If they are all high, we have a failure break. If we can stop just one of them, then we can stop the failure. So what we are doing right here at Doxsteel Fasteners, one of the many, many layers that we do to stop failure is modifying this environment. So the nickel-cobalt coating is not producing any hydrogen. So we can check that, and we have no failure. And I want to thank everybody, and thank you, guys.
All right, thank you so much, Omar. Now we're going to go ahead and turn it over to for the questions, for the Q&A session here. Give us just a second. I saw you've got some. I already see some questions there. So let me see what we've got here. Let's get a lot of guys asking questions. So let's go up to the top here. Somebody asked, where is the hydrogen coming from in the lower marine riser package in slide 10? So we'll knock over to that one right quick. Where's the slide thing? So slide 10, let me see, we'll go back. Let's pop back here. So yeah, so the failure number 2, Jim, where is the hydrogen coming from in the lower marine riser package?
So we see it coming from the zinc plating on the threads. There was a very good presentation from a colleague of mine when I was previously part of BP. Made a presentation in May this year in Washington, D.C. at a conference, I guess was hosted by Bessie. And they reported that the failures were all zinc related, except for the first one that I showed, which they reported as TSA or thermally sprayed aluminum. So that's the information I have, which was shared with Bessie.
All right. Our next question is Grebbing KA. They asked, thank you for your question, by the way. What was the exact hardness of the bolts in the 3 bolt failures?
I don't recall the exact hardnesses. In the second failure, I believe the maximum hardness specified was Rockwell C38 by the equipment manufacturer. In the first failure, there were 6 bolts there, and 5 of them failed brittly by hydrogen embrittlement. One of the bolts initiated cracking at 13 different failure locations. All those hardnesses were over Rockwell C35. The 6th bolt failed ductily, and its hardness was under Rockwell C35. So that was a pretty good field test, I guess, for hardness. The last failure, number 3, there was an amount of segregation that was a part of that bolting, and the segregation in the material led to high concentrations of hardness when heat treatment was done. So you'd have areas that were soft and hard and bolt, and the hard areas were as hard as Rockwell C42. So that would be greater than what guidelines are given right now in API 20E of Rockwell C34 maximum.
Okay, excellent. So Oscar asked, thank you for your question, Oscar. What is the external pressure difference between the riser connection, the lower marine riser, and the BOP?
What is the pressure differential?
Yeah, the external pressure difference between them.
Well, the first failure occurred around 3,000 feet water depth, so that would be roughly 1,500 psi water pressure. I don't know what the depths are on the other ones, but I would assume that they would be greater than that. Of course, if you look at just the calculations of pressure, the pressure is about half times the water depth in feet and psi. And if you use Henry's law, of course, you can see more hydrogen dribbling in at the deeper water depths than the more shallow water depths.
Okay.
Okay. Let's see. Christina asked, where is the atmospheric pressure involved in the diagram of slide 14? So let's get over to slide 14, see what she's. So.
Oh, was actually in the environment.
Yeah. So to answer that question, it's involved in the yellow circle, the environment or the amount of hydrogen that you produce or can drive in. And I'm not really prepared to discuss this in detail right now. The model that has been developed by the industry hasn't addressed this. It's extremely complicated, but it's based on the concentrations at crack tips, notch tips, the partial pressures, and of course the driving potentials. Typically, we find that the partial pressure of hydrogen at those depths may be over affected more by potential differences than by the partial pressures, although they are significant.
Yeah, I think that's related with what Steve Waite is asking.
Yeah, Steve asked down here, again, thank you for your question, said, so your Venn diagram includes hardness as the critical material property. We're also concerned with high strength as well, correct? I realize that there are correlations between UTS and hardness, universal tensile strength. I guess my question is, are we concerned based on UTS, not just hardness?
Well, the UTS is part of the stress, right?
Yeah.
Okay,
So really, very simply, there's a correlation between hardness and ultimate tensile strength. You can find it for high strength low alloy steels or bolting materials that are used here, like the L43. It's an ASTM E140. You'll have correlations between Rockwell C, Grinnell, and Vickers hardness in there. So yield strength, which is what people refer to more as a grade, the 125 grade being the minimum yield strength, there is a rough correlation between yield strength and UTS. In the higher strength materials, the correlation is the yield about 1.1 or 1.15 times the yield equals the ultimate. And I don't have any data to show that. That's a general rule of thumb. So I hope that helps you, Steve.
All right, so we've got time for maybe about one more question. I want to kind of get down and see if there's any that are related to the coding specifically so we can answer them. And for everyone who's asked questions, I mean, there are a lot of questions today, and thank you guys so much for asking questions. And we're going to go ahead and download all of these questions and post a download of all of our answers from our two experts next Monday. And I'll encourage you guys to join up into our Cost of Boat Failure LinkedIn group, because we'll definitely be posting them in there as well. But I want to get one question. Do you want to do this one?
Yeah.
Let's see here. Sure. Liliana asked, thank you for your question, Liliana. What happens to the hydrogen permeation if nickel-cobalt coating is damaged?
Well, that's a tough concern. What happens when nickel-cobalt? Since nickel-cobalt is a barrier coating, everybody's concerned about the damage or if the material is scratched and the steel is exposed. So as part of our testing here in Doxsteel Fasteners, and we're actually presenting these results in the following NACE 2018, we did also permeation of damaged nickel-cobalt, and we saw that there was no hydrogen being produced. Well, we didn't register or record any current. What happens is that the kinetics of nickel-cobalt is very slow for hydrogen. So even though the material is damaged and it's exposing the burst heel, in our test, I was taking out 7.5% of the coating. I was exposing 8% of the steel, and the production of hydrogen was not enough to cross the steel and to be detected on the exit cell. So that shows that even though the material, the coating is damaged, the kinetics is so slow that the hydrogen is not going to be enough to penetrate the material. That is not going to reach the threshold to be a damage on the material to produce hydrogen embrittlement. That's what I found.
And you guys at Doxsteel also take a lot. We take a lot of care in the shipping and packaging of the bolts as well, so
Of
they're
course.
not damaged before they go in.
And recommendations to users.
So,
Yeah.
so every effort, as Omar and Chris have said, are made to prevent this type of damage. Again, I think it's really important that the nickel-cobalt has in a way, an electrochemical healing way to block the hydrogen to move in there, as Omar has discussed. But let's recall now that when you look at risk from hydrogen embrittlement and avoiding the types of failures that I discussed earlier, you're looking for layers of protection. You're not looking necessarily for just one way of prevention, like using a bolt with a Rockwell C50 and then putting nickel-cobalt on that. You might want to think of using the layers of protection, using a bolt that has lower hardness that's been shown that doesn't fail, using a barrier coating such as the nickel-cobalt. Because in the third failure, the hardness readings on the bolts all passed because they didn't detect the zones of high hardness. The nickel-cobalt would form another layer of protection that would potentially have prevented that failure. So
Yes.
All right. Well, that's all the time we have today. And again, thank you guys so much for all of your questions. And we'll go through and take a look at them and give answers to them all and post a download of that come up in the following week here. Again, I want to thank everyone for coming out here to this first webinar we've done. We definitely want to do more. So if that's something that you're interested in, go ahead. If you're not registered for our webinars, go ahead and get registered and connect with us on LinkedIn and on all our various social medias, and definitely join the Cost of Bolt Failure LinkedIn group online on LinkedIn there. Lots of good discussion to be done. And yeah, thank you so much for joining us, and I hope you guys have a nice day.